chain rule. Now you can think about a function of f depending on x and y, and then x and y both depending on some other variables. Okay, you can think of, for example, x being like 2t, whereas y is t squared. And let's say f of xy is something like xy plus x squared plus 4. Okay. So in this situation, what I want to do is I want to know how f changes when I change the value of t. Okay, before I tackle this, I want to show you the difference between the single variable case and the multivariable case. So let me show you how things were done in single variable case. Note, in single variable case, if you had f of x equal to x squared and x equals to 3t plus 1. And if you wanted to know the change of f of change over change of t, it was simply the following thing. It was df over dx times dx over dt. This was called the chain rule, right? This is the Leibniz formulation of the chain rule. And it's very easy to understand because dx canceled and you have df over dt. So that's why it's the same thing. And you know how to do df which is just 2x. Right? And then dx dt is what? If you differentiate this function x by t, what do you get? 3. So you got 6x. So that's how you did the chain rule in the Leibniz way. Here was how we did it in the Newton's way. Newton's chain rule looked like you first plug this in here to make it as a function of t. So that's what f of t is, because x is same as 3t plus 1. If I replace this x by a 3t plus 1, that's your f of t. And then if you differentiate by t, you were to use the following terminology. Just think about this something squared as the outer function, so you differentiate that outside function. And then you pull the inside out and you differentiate that. Okay, so 3t plus 1, if you pull it out and differentiate, you get 3, right? Now, why are these the same? Well, they're the same because first 3 times 2 is 6. And x is 3t plus 1, so it's 6 times 3t plus 1. So they're the same thing. Okay. All right, so that's what we had in single variable case. Now back to this example. Here, the circumstance is more complicated because f depends on both x and y, and x and y both depend on this single variable t. So it's like this. Suppose, by the way, this kind of diagram is called the dependence diagram. Because it shows which variables depend on which. And these type of circumstances happen a lot in economics. So economics majors always try to learn multivariable calculus at least up to the chain rule. Because a lot of times, like what's the price of a cake? It depends on the price of the flour and sugar, right? But the flour and sugar may depend on what price of oil, who knows? So you have this dependence, and then if the oil prices go up, what happens? It costs more to make flour and also sugar. So they go up, and they both influence the final price. So that happens a lot in economics. And in econ, such a question is a valuable question to ask and answer. I mean, how fast would the price of the cake increase if you raise the price of oil? Like these type of questions can be asked all the time. And the way that the change of t will affect f is in two different paths. Right? And the multivariable chain rule tells us that when we are calculating chain rule for these complicated dependence diagrams, you have to take account into every possible path that one variable influences the other. And let me write down the formula for it. It's going to make more sense once you see the formula. It's like this. You first take the partial of f with respect to x, meaning that you don't consider any changes in y. You just assume that y is not changing and you're just changing x, and you want to see how changes, the final price will be affected by the changes in the price of flour. Okay? And then you multiply this by change of x with respect to change of t. Now notice that here I'm using d, not round. It's not round x over round t, it's dx over dt. That's because x is a single variable function. In that case, you use d. But f is a multivariable function, and you're doing a partial derivative, so in that case, you have to use the round. Now think about what this is doing. It's like you're trying to figure out how the change of t is affecting the change of f going through x. That's how you understand it, right? But that means you're only figuring out what's happening over this side, right? And that's not enough. You have to consider the other case where f is being affected by y, and you have to think about how y is being affected by the change of t. And if you multiply it, you get this. So knowing that we should consider this quantity and also this quantity is not that surprising. The surprising thing is when you think about how we should combine these two information, that the mathematicians realize that you can actually prove that a simple addition is enough. If you just simply add the two quantities, you will get the total change of f brought about by changing the value of t. So this is called the multivariable chain rule for this dependence diagram. By the way, if you have more variables, then you'll have more complicated chain rule because you have more different paths that one affects the other. Okay? Now let's see what that gives us, and we want to actually verify that this rule is true. I don't want to prove it, I just want to show you that it's true. So let's actually calculate it. Let's see, what is round f round x? You're trying to differentiate by x, right? What's that?
Y.
1 y.
So if you differentiate x, it's 1, so it's 1 times y plus 2 times x, and 4y differentiates to 0. So that's round f round x, right? Now what's dx dt? If I take the derivative of 2t, what do I get? 2. Okay. So we got the first part, okay? Plus, now we have to differentiate this by y. xy differentiates to, if I differentiate by y, what do I get? Y differentiates to 1, right? X is just a constant, so x times 1 is x. And x squared differentiates to 0 because we're differentiating by y. 4y differentiates to 4. And then what's dy dt? 2t. So apparently that's our answer. So let's try to simplify this. It's 2y plus 4x plus 2tx plus 8t. A lot of times, if you actually want to evaluate this for specific value of t, you want to replace x and y by these 2t and t squared, because in that way you can simplify it in a readily usable form. Right? So this is y is 2t squared, so let me replace it. X is 2t plus x is 2t. So that's 4t squared, 2t squared is 6t squared. 8t, that's 16t. So that's what the chain rule claims. The chain rule claims that the answer to this question, how fast f is changing when you change the value of t, is 6t squared plus 16t. Now let's see what happens if we actually directly calculated it.
Do you have to break it down any more than that? Like take a t out and take it?
I mean, you
What was
can
that
factor the 2t out. That's a possible simplification. It depends on the context. I mean, usually you want to simplify because you have the next question to solve using this.
Okay.
I mean, if it was trying to figure out when this derivative is equal to 0, then you would factor it. It depends on the context.
Okay.
All right, so I can also do this. I can think about what the function of f is for the t by replacing x by 2t and y by t squared, right? So what's that? 2t times t squared plus 2t squared plus 4 times t squared, which is 2t cubed plus 4t squared, 4t plus, that's 8t squared. And now, because I know f of t, what's df dt? Three comes down to 16 squared. 2 comes down. Oh, so it's the same, right? So we
can we do it this way?
Of course, if it's explicitly given, then you can definitely do it this way. And of course, I'm going to twist the questions on the exam so that these are not given, rather something like this is given, and you have to use, you're forced to use this. So you can't go around not knowing this. It's a very important theorem, okay? In fact, maybe your friend who is majoring in economics might come to you one day and say, can you explain what the chain rule is? And then you really have to explain to him.